Let's talk about hydrogenation of alkynes now. So here I've got an alkyne, 2 pi bonds instead of 1. If I hydrogenate it, you might guess that I'm going to add the hydrogen across one of these pi bonds and end up with some alkene like this. And you'd be right, but the problem is that there's no way that I can stay there, right? Because this is just as reactive as this is. So under the conditions, I'm not going to be able to stop this. It's going to go all the way to the alkane. Okay, so I got to keep that in mind. If I'm going to hydrogenate that alkyne, I'm not going to be able to just throw catalyst and hydrogen at it and get it to stop there. It's going to keep going to the alkane. There is a solution to this. What if my catalyst was bad? If my catalyst was bad, then maybe I could only get this far, and then it wouldn't be able to take it the rest of the way. And that actually got developed, I think, in the 1960s. So I'm going to give it hydrogen again, and then I'm going to give it something called Lindlar catalyst. Lindlar catalyst is this weird mix. It's palladium, it's not on carbon, it's on barium sulfate, I think. There's lead attached to it because lead just kind of makes all catalysts worse. There's even some quinoline, which is some weird tree bark derived benzene plus nitrogen looking thing that also messes with the catalyst. So it's basically a bunch of things that we poured into it to make it work bad. So with Lindlar catalyst, now I can only attack once and stop at the alkene. And to be actually more clear, let's say I had some internal alkyne. If I treated this with hydrogen and Lindlar catalyst, not only would I stop at the alkene, but I would end up with the cis alkene, not the trans alkene. Why is that? Well, it gets back to why palladium on carbon or other solid catalysts, heterogeneous catalysis, right? Catalysts, they're going to deliver hydrogen to the same face of the molecule, right? So I've got my surface, my molecule is going to dock on my surface, and my surface is going to deliver 2 hydrogen atoms to the same face of my molecule. All right, so I'm not going to get any trans, it's always going to be cis. My hydrogens are going to the same face. Can I make trans alkenes? Not like this. I cannot make trans alkenes by catalytic hydrogenation. I'm going to have to come up with some fancier way to do that, and we won't get there for many, many weeks. So again, hydrogenation of alkynes. It's very easy to over-reduce, over-hydrogenate, and get all the way to the alkane. If you want to stop at the alkene, you need a bad catalyst. And this is bad. Welcome back to Etymology Corner, the corner where words come to life. This is hydrogenolysis. I can see 2 words, or 2 roots, in this word. Lysis means to cut, right? Like electrolysis or cell lysis. Hydrogen means hydrogen, the atom hydrogen. So what I'm talking about here is not hydrogenation, the addition of hydrogen atoms. Here I'm using hydrogen to cut. So you can kind of envision this as me cutting weak bonds in half and then cauterizing the ends with hydrogen atoms. So here's a really great example of this. We're going to learn next week maybe, or the week after, sometime, we're going to learn how to make a nitro compound. So nitro looks like this. If I draw it out, it would look like this. So this nitro compound, if I treat this with palladium on carbon and hydrogen, I'm actually going to end up all the way reduced to an amine. It's pretty awesome. How does that work? Well, you can imagine this as, it's a pretty complicated mechanism, but essentially I'm going to first hydrogenate that bond, and then I've got NO single bonds. And NO single bonds are very weak. And that's the kind of thing I can break with this hydrogenolysis, right? So with my catalyst, I'm essentially cleaving that bond in half, right? So this is what we call a reduction. I'm reducing my nitro to my amine. I can also do this with, say, and this is more of a pure hydrogenation, but a nitrile can be reduced all the way to an amine as well. Another one that seems less useful until you think about it, I can reduce azids down. So azid coming in is easily reduced all the way down to an amine. So why is that useful? Let's go back to SN2vil, right? So let's say I want this amine, okay? Now, can I get there from the bromine plus NH2, NH3, sorry, right? Would I be able to use NH3 to attack here and make that bond? Well, yes and no, right? This is a good nucleophile. This is an unhindered electrophile. This is a great SN2 reaction. But the problem is that this is still really reactive. So it wouldn't stop there. It would find another bromide and would keep going, right? So it would go, and maybe I would end up with like 3 on here. Some cases I might actually end up with 4 and end up with the N plus Br minus. So this is not a great way to make this. It's much, much easier for me to take that bromide, react with sodium azid. Again, azid is a great SN2 nucleophile. Get the azid compound. Are they explosive? Yeah, they're a tiny bit explosive, but just like watch out, right? Just kind of take it easy. Just take it easy, all right? Keep it cold. Maybe don't concentrate it. The larger it is, the safer it is. But these azids, again, are easily reduced by this method and a few other methods to the NH2. So that's why that's why this might be important. But hydrogenolysis, again, I'm cutting weak bonds. In these cases, I'm cutting a weak bond between N and O. In this case, with azid, you can imagine cutting weak bonds between N and N, right? So any bond between 2 electronegative atoms is going to be weak. So both of these are really nice ways to make amines. 2 other common hydrogenolysis reactions that look a little bit different. So here, if I remember my benzyl group, benzyl, hard to remember, but it is a benzene ring next to a CH2. So just the ring itself would be phenyl, but with the CH2 next to it, that's benzyl. If I have a benzoamine or a benzyl ether, and I treat these with hydrogen and palladium on carbon, I'm actually going to chop it at that benzyl bond, there and there. And I'll end up with this methylbenzene, or also called toluene, and I'll actually get an amine or an alcohol out of that, depending on which one I start with. So I bring this up because as you get into peptide chemistry, if you're trying to like make a long chain of amino acids into a protein, or if you're doing more complex organic synthesis, you often have to do this to kind of deprotect. So you might have this benzyl group on an amine to kind of cover it up, almost like masking tape covers up the part of the wall that you don't want to paint. And so hydrogenolysis was able to take this benzyl off. Why is this a weak bond? Why is that a weak bond? The reason the benzyl bond is weak is because that radical, much like if it were a cation, is really stable And it's really stable because, say it with me, of resonance, right? So I'm able to delocalize that electron all over the ring. And so that makes that very stable, which makes it relatively easy to break that bond. So hydrogenolysis, using this catalyst and hydrogen gas to break weak bonds. Could be NN or NO bonds, or it could be bonds to a benzylic carbon.